So good afternoon, everyone. Good afternoon, and I hope you are well settled in your seats now. So I am Shaumik Siddhanta, an assistant professor in the Department of Chemistry here at IIT Delhi. So it's a pleasure to extend a warm welcome to each of you on behalf of the Academic Outreach and New Initiative Office at IIT Delhi. For many of you, this might be the first visit to our campus, right? Okay, so and we hope that you enjoy this vibrant and inspiring environment we have here at IIT Delhi. So first and foremost, I would like to express my heartfelt gratitude to our Director, Professor Banerjee, Dean of Academics, Professor Kurur, and our Associate Dean of Outreach and New Initiatives, Professor Subodh, whose vision and support have been instrumental in bringing this program to life. I would also like to recognize the dedicated efforts of our staff, Gaurav, Renu, Ajay, and Shaksham, whose relentless work behind the scene has made the event today possible. Last but not the least, a big thank you to the CAIC team and our student volunteers for their unwavering support and enthusiasm. Today, we are thrilled to launch a new initiative, ANVESHAN, UG Engagement Series. So this program represents an exciting journey designed to bridge the gap between IIT Delhi and the dynamic undergraduate student community in our region. Through ANVESHAN, we aim to create opportunities for you, our promising young scholars, to engage with the world of research at IIT Delhi. Our goal is twofold. First, to introduce you to the innovative research and learning ecosystem here, inspiring many of you to consider IIT Delhi for future postgraduate pursuits. And second, to foster meaningful connections and collaborations with nearby institutes, creating a network of knowledge and shared exploration. ANVESHAN will offer a variety of events such as interactive sessions, panel discussions, case competitions, and specialized workshops. These monthly events are designed to spark curiosity, nurture innovation, and build foundational skills, providing a glimpse of the possibilities that await within the realm of research and higher education. Our first event in this series is to kick off with two lectures by Professor Rajesh, Prasad, and Professor Abhijit Majumdar, and we are excited to have you on board for this journey. We hope ANVESHAN becomes a platform that inspires, educates, and connects. Thank you for being here today, and we look forward to your participation and support in making ANVESHAN a resounding success. Now, I would like to invite Professor Narayanan Kurur, the Dean of Academics at IIT Delhi, to light the lamp and also speak a few words and formally inaugurate the event. I also invite Professor Rajesh, Prasad, and Professor Abhijit to come on the stage for the lighting of the lamp.
Afternoon. I'll have some questions initially, not difficult. With a show of hands, can we know how many of you are here for the first time? Wow, that's a lot. We hope that you will get some time for you to explore the campus. We have a fantastic campus which is very different from the rest of Delhi, I think. I am a little bit surprised that it is your first visit, because many Delhi college students would have visited us 2 weeks ago when we had our cultural festival, I would have thought. But I guess you are not. You are all interested in science, technology, engineering and medicine. So how would you come here? No? Okay. All right. How many of you are in your first year of undergraduate education? Undergraduate program, I guess. Okay. Okay, so those were easy questions in any case. We are very excited about outreach and new initiatives unit of the Institute. Programs. 3 have been long existing, physics, anymore. Well, we never were completely only engineering. We've had science programs, and we are not the only IIT. All IITs have it. So I would recommend that all of you go and Google JAM, not JAM as in Joint Admission Test for MSc, which is what you'll have to clear to come to one of the IITs for postgraduate education. And we hope that this, if nothing else, gets you thinking about IIT as a destination for postgraduate program. We also have PhD programs, so you should consider IIT seriously for higher studies. And we are hoping. So we have a similar program we do for school students. And this outreach cell, which we have, is essentially our way of sort of keeping in touch with the society. It's what we give back, and it is to raise awareness about IITs and about science, technology, engineering, medicine. We also have management, etc. And so that because we hear often that students are unaware that these things existed in IIT. So this is a way of getting you, when you are young, to know about the things that are there in front of you, so that you could choose this. So this is an initiative. Soumik Siddhanta had introduced some people from the academic outreach who are the ones who are responsible for it. So maybe I can just get them to come on stage so you know who they are. They are the ones who do all the hard work. Gaurav is the one. Please, Gaurav. There's Saksham there. Renu. Ajay is there. Soumik runs this program, which is called SciTech Spins for undergraduate students. We have a similar thing for also high school students. We have other programs. We have a STEM mentorship for girls, where we take 30, 40, 50, 60, 100 students now, and take them when they are in their 9th or 11th class and get them to come to us on a regular basis, all in the hope that we can encourage people to stay in science. So the hard work is done by them. Nirmal is, well, he is also outreach and he is also part of our office. Nirmal is an all-rounder. He does many things at many places. And their boss is the academic dean, outreach and new initiatives, associate dean, Professor Subodh Sharma, who is unavailable today. Otherwise, he leads the pack. Okay, so this is something. These are people. There are a lot of, yes, of course, there are a lot of volunteers. I think we'll fill up the stage if we had all of them here. And many of, well, today is a class day for us. So in any case, so these are the people. So I think big round of applause for them. Thank you. Thank you. So we hope that with this program that we can get more of you to get excited to stay in STEM, to continue your higher studies at one of the IITs and maybe even IIT Delhi. There are 23 of them, 23 IITs, so you should consider higher studies. It's an attractive option, of course. We don't know what the state of the 2-year MSc programs would be soon, but nevertheless, I think now it still exists. So we hope you have a good time, that you learn something out of this. And today we have two of our best teachers in the institute, Professor Rajesh Prasad and Professor Abhijit Majumdar, who will show you things that are related to science, to relate science to things that you either see translational as in the Bulletproof vest, or things that are typically known to us, I've heard about, and what is the scientific basis of all of this. In the future, we hope we can also get you to do some things hands-on, depending upon the sizes that we can take. But once again, it's a very great pleasure for us to have all of you here. Yeah, we realize that it is the weekend before Deepavali, and DU is having a break starting today. So there might have been people who might have been interested but have chosen to leave because of the break. But let's hope you can tell your friends about IIT Delhi and have them come next time around. Thank you very much and have a good time.
And I'm sure that all of you are very excited about the event and the talks today. And it's our pleasure to have with us Professor Rajesh Prasad, Professor at the Department of Material Science and Engineering with us today. So he also served as the head of the department until very recently. So he holds BTech and MA degrees from BHU and Indian Institute of Science respectively, and PhD from University of Cambridge. He has been also awarded Distinguished Alumnus Award from BHU and Teaching Excellence Award here at IIT Delhi. So his primary field of research involves physical metallurgy, phase transformations, metal forms, and others. So today he is going to talk on a very interesting topic at the intersection of material science and engineering. The title of the talk is The Sinking of Titanic, How Things Deform and Break. Okay, so without much further ado, let me welcome Professor Prasad on the stage.
Starts. In addition to all the things that Professor Siddhanta said, Rajesh Prasad is also an avid photographer. That's also to tell you that people have a life outside of science. So you can still have a life outside of science. He is an avid photographer, and he knows about pretty much anything, and is a very, very good friend of mine.
Let me correct, not a photographer, a bird watcher.
Watcher, okay. Well, even more time. Do it right away because I might not stay till that talk. Professor Abhijit Majumdar is an avid footballer to the extent where he broke his knee while playing for the institute. So we do all sorts of things.
Thank you, Professor Kurur and Professor Siddhant for this invitation. It's always. You are able to hear me? Yeah. So thank you very much again for this invitation, and it's always a pleasure to talk to young students and future scientists and engineers of India. So let me introduce my department, because it's not a very common department in all engineering institutes, and in IIT also it's a young department. So we are only 6 years old, the Department of Material Science and Engineering. In 2018 we started, and we now have 3 programs, one in BTech and 2 MTech programs, and of course there is a PhD program where you can join. And this is, our department is very interdisciplinary, So for a PhD program, we accept people with background in not only in material science and metallurgy, but also in physics, chemistry, and other engineering disciplines. Sometimes we make news for good reasons. So there was this time capsule thing in which letters written by young people were kept in a. My spring festival is not some real mechanical spring. So this spring festival is a different kind of festival. These are small springs. You will not be able to see if you are very far back, but there are seats nearby. So if some of you want to move nearby, you can do so now while I set it up. Maybe if somebody can hold it for me. Could help. Can you come? Can you come from that side? Hold it and you just take it. Okay. You take it. So there are two steps. Can you go here? Although you have been me. Thank you very much. Take all out the effort. So that it doesn't fall here. Okay, so the springs are, so I hope those with good eyes will be able to see from the back also. So let the spring festival go on. The topic for the lecture is actually a little depressing, and because we are talking of deformation and breakage and fracture, all sorts of negative things, but you have to get to know the mechanics behind these things to avoid them. So the goal of engineer is to avoid all these kind of deformations, or sometimes they want this deformation also when they want to shape material, so you want plastic deformation. But that's the main topic. I will like to recommend, better than this lecture, if you can read why I am not going through the flow. How you may like that to happen, but we are not going through the flow. I am giving you two options. I am not going through the flow because flow is rigid. Rigid means non-deformable, or actually the opposite of that, the floor is deformable. So show by your hand how many of you vote for floor is rigid. You have to vote one of, you can't keep your hands down for both the options. So floor is rigid and floor is deformable. I think there are more people for floor is deformable. So let's look at, this is your class 10 or class 11 mechanics. The question makes significance only because actually we know gravity exists and gravity is pulling down. That's what makes the sense that why, the sense of the question, that why we are not going down. Because something is pulling us, then something should be resisting this pull. And we all know that there is a normal reaction. The floor is applying a normal reaction which is balancing the weight. The source of W, the weight, we know that is due to gravity. What is the source of normal reaction? Where is normal reaction coming from? The floor is giving the normal reaction, but by what mechanism? Little bit more, yeah. You can participate loudly. I think maybe we can circulate mic also if somebody can help. If somebody wants to participate, then it will be more interesting. Can we circulate mic? If somebody wants to speak, raise your hand, we can give you the mic. So, the source of normal reaction, let us see, actually, so those, now we are coming to the answer. If the floor was rigid, there is no mechanism in the world which will generate the normal reaction. So, normal reaction cannot be there on a rigid floor. The only mechanism by which the floor generates this normal reaction is that floor deforms. Floor deforms like a spring. And when a spring deforms, it puts an upward force on an object which is deforming. Similarly, the floor is deforming and it is putting an upward force, the normal reaction. So, the normal reaction is actually elastic deformation force. Elastic deformation force of the floor. What is our spring doing? Oh, what's the time now? 2:55, about 10 minutes. It seems, I don't know if all of you are able to see, it seems one spring is growing. One spring is nice and happy and satisfied spring, but one spring wants development in its life. It's growing. Now, again going back to your class 10, weight and normal reaction. This is a very interesting question. Weight and normal reaction are equal and opposite due to? Okay, raise your hand. First law. Second law. I can see some hands. Third law. All the hands. We will come to the answer. So, normal reaction is produced by elastic deformation. So, actually, this rigid body or rigid body mechanics which we teach you is actually a fiction. A fiction created to simplify our understanding, but is not reality. So, in the same book which I recommended to you, this quotation is there. There is no such thing as truly rigid material, springiness being property of every structure and every solid. Now let's come. Weight is due to the gravity. What is the law which governs gravity? Newton's law, you know that. Normal force is due to elastic deformation. Which law governs elastic deformation? Which law? You must have heard. Young's modulus, yes, Young's modulus, but that's the modulus, not the law. Hooke's law. Hooke's law. Hooke's law is the law that governs elastic deformation. So I give you a quiz in which the first question you have already answered. Who gave us the law of elasticity? Robert Hooke. But I throw 4 more questions to you. Who was architect and town planner of London after the Great Fire? Who was assistant of Robert Boyle? Boyle's law. All of you have studied. Pressure is inversely proportional to volume if temperature is constant. But somebody needs to measure that pressure and measure that volume and to make instruments to test this law. Who did that for Robert Boyle was professor, he needed some assistant to do that. And who accused? We just said that law of gravity Newton, but in Newton's own time, he was accused of plagiarism and not without any basis. So, who accused Isaac Newton of stealing, that you have stealing my gravitation idea? I have that idea before you and I have shared it with you. Who wrote the first book on optical microscopy? The thing is, that answer to all these questions is just one, Robert Hooke. You can see the genius. You can see the genius of the person at the same time contemporary of Newton, maybe not as famous as Newton. We know him only through his Robert Hooke, but he was town planner of London, and he contributed this monument. If you go to London, or if you have visited London, one of the famous monuments of London is the monument which remembers this great fire. And that monument was designed and built. The architect for that monument was Robert Hooke himself. And on the left hand side, you see the microscope he was using, and he wrote the first book on microscopy called Micrographia. And he showed how to use optical microscope for studying material. Of course, we are interested in the Hooke's law, but why was, it's another interesting question, why was Robert Hooke interested in the deformation of a spring? Of course, he was a mad person, as you can see. He was interested in so many things. So he was interested in spring also. But what was the reason why he was interested in a spring? Because he wanted to help sailors determine their longitude at sea. Another story, I leave it to you, Google it and find out. But I want to share one more interesting thing, one very, very interesting thing. Hooke's law, such a boring law, F is equal to K delta L, force is proportional to elongation. So simple, so ordinary. But how did he announce to the world that I have discovered the law? That's very, very extraordinary, and I can't resist sharing that. So he wrote a paper on helioscopes. Now see his interest. He wants to look at sun, and he wants to look at sunspots. Any of you who are interested in science, and when a solar eclipse comes and you want to look at the sun, everybody warns you. You can't look directly. You have to take enough precaution. So looking at the sun requires special telescopes which will not spoil your eye. So he was designing these telescopes and called helioscope, and he wrote a paper on it in 1676. In the paper, because he is such a multifarious person, so many interests. So after describing helioscope, he gives a list of 10 items. 1, 2, 3, 10. 10 items that these are the things I am working on. I will write papers on them in future. Future one. Any of you who will be doing PhD, or if there are any PhD students in this group, you will know that when you write thesis, you write in the end, the last chapter of the thesis is always future work. That what all can be done in future. So in the research paper also he wrote list of 10 items of future work. Item number 3, the true story of elasticity and springiness. So he is announcing that I have discovered the true story of elasticity and springiness, but not in this paper. Paper is coming later. But in this paper, he gave a hint. Hint for you to decipher. Hint for the world to decipher. This word. Sayinostu. It's not English, it's not Greek, Latin either. It's a Latin anagram. Anagram of the law. So this is the first form of Hooke's law. This is how Hooke's law is published for the first time. This anagram. If you can, so the Hooke's challenge. If you can decipher this anagram, you know the law I have discovered. If you can't, you don't. समझने वाले समझ गए, जो ना समझा वो अनाड़ी. For 2 years, the world remained anadi. Nobody could samjho what this Sayinostu stand for. So happily, after 2 years, he deciphered the anagram for the Janta, that ut tensio sic vis As the tension, so the extension. Now, I forgot, I let you raise your hands, but I forgot to tell you about that action-reaction thing. So the most hands raised for that the normal reaction and weight are equal and opposite due to third law. But please remember, please Google and please go and look at your textbook. Both forces are acting on the same body. Action-reaction pair never act on the same body. So although they are equal and opposite, they are not action-reaction pair. Somehow I was thinking that there is a slide on that, but I missed it. So those minority who are saying first law are actually the right one, because here the acceleration is 0, and for 0 acceleration there should be net 0 force, and that's why the two forces are equal and opposite, not because they are action-reaction pair. So now we go to last year's Father's Day, June 18, and that was a disastrous day for a father and son. You remember? Anybody remembers why it was disastrous for a father and son? Yeah? That's an interesting answer, but I will show you. Now you remember the news about father and son? Yeah? Now you must be remembering, because this was an important news that time, that 4 people went in a submarine under the sea and they were lost. They never came up. This was their submarine, Titan. What was their destination? Where were they going? They were going to find out Titanic wreckage, 3.8 kilometers under the sea. Now, what was so interesting about Titanic that they were trying to discover? Now it's becoming a tourist place, it seems. So, Titanic, as you must be knowing, but just to share you some important details, in 1912, the name Titanic itself was selected because it was of exceptional strength, size and power. This is the literal meaning of Titanic. So it was one of the largest and the most luxurious ship which was created at that time. 230 meters long, so many kilos, I can't read it, 46,000, 600 tons of coal per day was burning to run the ship. So it was losing 600 tons of weight every day. And interior, the nice luxury 5-star interior, doesn't look like a ship. But technologically, most important thing was that it was claimed to be unsinkable. Why unsinkable? Because it was designed to have 16 watertight compartments. 16 watertight compartments, and the claim was that if water fills in one compartment, it will not go into the other compartment. That's the meaning of watertight. And if many of these, 4, 5, 6 of these watertight compartments get filled, the ship will be still floating. So to sink the ship, you have to fill all the 16 watertight compartments. That appeared to be impossibility. But you know now the truth. What happened in the very first journey, starting from Southampton, the Titanic was supposed to reach New York on 17th April, but 2 days before that, on 15th April, it hit an iceberg and sank. So Titanic hit an iceberg and sank and broke in two. Now, what is the ship hull made of? What is the ship hull made of? What material? Titanic, the steel rope, that also ship quality steel, that also one of the most advanced ship which was ever commissioned or ever launched in those days. What was so dramatic, or what was so special? Why did Titanic sink so easily? It's a real surprise. But I think, I'm not giving you a nice after tragedy. So that father-son tragedy, now Titanic tragedy. Now let me come to yet another tragedy, Space Shuttle Challenger tragedy, 1986, more modern. And again, see, Titanic designers thought that nothing can happen to their ship, and it could not complete its first trip. Space shuttle designers at one point in 1986 thought that now they have improved their technology so much that they can run it like a bus. Jao aao, you can buy a ticket and go. To prove this, they said that you don't even have to be an astronaut or something. You just show your interest, we will send you up. And so in the crew, they selected one history teacher, high school history teacher. No, not even high school science teacher, high school history teacher, particularly to prove that point, their point, that no science, technology or engineering is required to be an astronaut. We will train you, we will send you. So this teacher was selected. She actually made a lesson, history lesson, which she was supposed to broadcast while in space. But unfortunately, that never happened. 78 seconds after the launch, everything blew up. And none of these crew members survived. Again, what happened? So now, let's take, I have an interesting demonstration for you, a liquid nitrogen, a liquid which has a temperature of minus 196 degrees Celsius, something coldest you will ever come across. So, can we have a liquid nitrogen in this can you can take? Don't let the liquid contact your body. Okay, that's the only thing of the day. What is our spray doing? So it's not stopping from growing. So now it's 310. So very dynamic spring. It's a metal spring. It's a metal spring. Any of you can come up. Liquid nitrogen being poured. So what is that? It's the right. Your name? So you are in which department? I want to share a tragic personal history. So when I was young, I had a sweetheart. And Valentine's Day came, so I thought, let me be different from Janta. Everybody gives red rose. I'll give a bright yellow big one. So it will impress her more. And I thought that I would, rather than presenting in the classical style, I will do a balancing act and present it to her. When I did that, she was not impressed by my balancing act. And she was not impressed by the yellow flower. Everybody gives red rose. What is this yellow flower doing? This is what it is. Practically. But they put it in the liquid nitrogen, took it out, and it's This material is very cheap. That's why we are wasting. It's cheaper than milk. And we have a plant. In IIT we have a plant. तुम्हारा ग्लव्स का अच्छा ग्लव्स का है अब ग्लव्स की जरूरत पड़ेगी -196 Hello. So see, at the same thing, which is so nice and flexible at room temperature, is becoming like papad. Like papad. But what about this rubber tube? Let us see this. That was biological organic material. Now we have some sort of a polymer, which also is organic in a way, but it's not a flower. Not able to bend it. Broke like a glass. Rubber tube broke like a glass. How will it happen? I didn't know you. You are in my class. Jada baat bula diya. Kaya bhi chota ho jayega. You also have balloon. We will do an experiment with that. Keep that. I think it is. Ask them to gloves and whatever. छोटा हो गया है अब इस पर एक उधर पीछे रखा टेबल पर very it's nitrogen. We are breathing all the time. So it's not a pollutant or it's not dangerous otherwise. Only dangerous thing is the temperature. -196, so just like you saw, the flower became brittle, my skin will become brittle in the same fashion. That's also an organic material. So if I have direct, you should avoid direct contact. That's why I use gloves and all. So the only safety precaution required is that you should not get it on your body. But otherwise, breathing or going into the air is not really dangerous. It's always looking like a fume coming. Okay, I think it has become so small now. It has forgotten its back. तुम बलून हो, अपने स्वरूप को पहचानो, वापस आ रहा धीरे धीरे अपने पूर्व स्वरूप में आ रहा. So this was just for fun. This is not big science. This is your PV is equal to nRT. जब T कम था तो V कम हो गया, अब फिर से रूम टेम्परेचर पर आ गया, it has gained its volume. What you have read as Charles law or ideal gas law. So, it is now not much of use. This is the viscosity of volume. Then it put on a hot surface, so it's evaporating. It actually forms a small droplet. It forms a small droplet, you see. So that's a nice fashionable name. Leading, you can create in your home, make the tawa very hot and then put water. Then the water droplets will form and will spin. It's very hot for the liquid. And I'm pouring the liquid on that, so it's evaporating. Demo which you saw, this simple rubber tube which became glassy on becoming cold was the reason behind challenges design. If sun is falling, it will be extremely hot because there is no atmosphere. And on the shade side, it will be very cold. And what rubber does at cold temperature, you have already seen. But what I have not demonstrated to you and what I can't demonstrate to you here is about metals. Even metals at low temperature become brittle. The metal which is deformable is flexible. You can hammer it and it will not break. It will only deform like steel or aluminium or copper. If you hammer it, it will change the shape. It will not break. But if you take the steel to low temperature, just like your rubber, this also becomes brittle. I am showing you a graph where the y-axis is energy absorbed in fracture and x-axis is temperature. Energy absorbed in fracture, ताली बजा लो. So, energy absorbed in fracture is a measure of how brittle the material is. Brittle material will absorb very less energy. That's why they break so easily. Whereas ductile material will absorb more energy. So on the green side you have ductile, on the brittle side, on the red side you have brittle, low energy absorption and large energy absorption. But what you showed here is special material which are becoming brittle at low temperature. But same material can be ductile at high temperature but brittle at low temperature. You are getting answer for Titanic disaster. That the ship was going in cold water. Ductile to brittle transition of metals were not understood at that time. Nobody thought that what in the shipyard is a very ductile steel in the cold ocean can become brittle. So later on, when Titanic wreckage were discovered at the bottom of the sea, some of the pieces were brought to the lab, and Titanic at high temperature also was not as ductile as the modern steel 836. But at low temperature, Titanic steel is becoming brittle even at higher temperature than the modern steel. So, in cold sea, the material can become brittle. These are the tested samples. Another indication of brittleness is that brittle materials will show reasonably flatter surface. When glass breaks, it has a nice flat surface, isn't it? Glass is brittle. So reasonably flat surface, whereas if the ductile metal breaks, it will give you a rough surface. So the two test is also confirming that Titanic steel was not a good steel composition wise. So composition of steel of Titanic made it susceptible to ductile to brittle transition. You have already seen ductile to brittle transition in flower, in rubber tube. The same thing happened for steel. Now time has come for your balloon experiment. So please take out your balloon and blow it. All of you have got. ये तो मान नहीं रहा है। एक प्रैक्टिकल टेस्ट लिया, इसके बाद तो देख भी नहीं सकता हूँ। एक्सपेरिमेंट शुरू हो गया, यही एक्सपेरिमेंट है। डोंट बी एम्बैरेस्ड। So now Now your attention. This was not Diwali Pataka. This was a very serious experiment. What you are trying to do is to put a hole in the balloon. You are trying to prick a pin. Why didn't you create just a hole? But the result is that the whole surface tore and tore with a burst. This is called fast fracture, and fast fracture is very, very dangerous, as you can see in engineering components. In balloon it is a pleasure and it's fun, but in engineering component if it happens, this is very, very dangerous. So those of you who cycle will know this. Sometimes when you are cycling, the tube bursts with like balloon with noise. Sometimes when you have rode the bike nicely, you came home or you came to the hostel, put your bike, next morning you came, or after 2 hours you came, the air is gone. Air was there when you were riding and when you came, but the air is gone in 3-4 hours. So there are two ways. One is the silent puncture. Both are failure of the tube. In both cases you will have to run to the cycle wala to get repaired. But in one case it is silent puncture, another case it is a noisy burst. What is the difference between the two? So we will do some paper tearing experiment. I have a sheet of paper. Now I do a tensile test. Tensile test means I put it in tension. So it's a strip of material. This is a tensile test actually being done in the engineering labs. When you want to test any material, the strength of any material, you take a sample, you take a strip or you take a cylinder, put it in grips and pull in tension. So I am putting the paper strip in tension. And my testing machine is my hands. So I am pulling. But I am not able to tear. I am not able to tear the paper. I am too weak. I am old. With a lot of force, I could tear it, and the tear happened in the grip, not somewhere in the middle. I introduce a small crack, a small cut on the top edge, and now I do the same test. I require a little bit more force, but much less than without crack. Now I make a little larger crack, and I try to pull. very easily. So the fracture stress, what this is giving you a message, that fracture stress is not a material property. Material is the same. So it's material plus crack property. Whether the material or the component is having a crack or not, and whether it is having a small crack or large crack. Larger the crack, easier to tear it. So the fracture stress depends upon crack size. So if no cut is there, it will be very strong. A small cut is there, it's weak. Larger cut, very weak. You can do this experiment at home and see for yourself. But another experiment now. I have a crack, but instead of pulling it in tension, I compress it. This is big engineering, big science. I try to compress, then the crack will not grow. The two faces, instead of opening, the crack two faces, which will open in tension, if they are in compression, they will come together. So they are trying to come together. So I will never be able to tear the piece of paper, however high compressive stress I apply. But tensile stress, it's easy. The method. That's the engineering design method. That if you want to avoid a crack to grow, put the crack in compression. And this is what is done. So in tensile stress, crack grows. Compressive stress, crack does not grow. And the conclusion is that tensile stress leads to crack propagation. Compressive stress is safe. This simple conclusion is the advanced Gorilla Glass on your mobile phone. Now mobile phone is your sheet of paper, which you don't want to tear or crack. But cracks are anywhere present because of wear and tear. When I say crack, it doesn't have to be very large crack. A micron-sized scratch also will act like a crack and has a stress concentration. And when you put load on it, it will easily crack. So one way of making these mobile phone glasses or TV screen or any such glass object where you don't want fracture, where fracture is dangerous and unsafe. So you introduce, there are technology by which you can introduce already on the surface compressive stress. I am not externally putting, that's why the phrase residual. Residual means it is automatically there. The material has been processed so that it will have compressive stress. Now when you put tensile stress on that, you are only cancelling the compressive stress. Unless and until overall it will go into tension, the material is safe. So this is one way to make safe material, and two technologies are known for glass: ion exchange method and tempering. And one technology is known to civil engineers for long. So that's why they use arch bridges instead of a flat bridge. When you put stone on two pillars, the stone will bend due to the weight. And in bending, whenever you bend, whenever you bend anything, the convex side will be in tension. The concave side will be in compression. So the tension side will be dangerous. Something is ringing, I don't know. My phone? Yeah, my phone is ringing. Yeah. It is a strange kind of ring which I never had. So new things are happening, you see. Should always be ready. Yeah. So when civil engineers design concrete is also a brittle material. And if you put concrete in tension, if you put stone in tension, you are inviting disaster. So the way to design with stone and concrete is to put them in compression. And this is what happens when you put the stones in an arch form. So this top, focus on this top arch, the top stone, which is called the keystone. Now, by gravity, the stone can only fall. But it cannot fall because there are two other stones on the side. So for it to fall, it will try to push them outward. Now the Newton's third law comes in. The central stone is trying to push the side stones outward. The side stones, the reaction force will try to push it inward. So the central stone is in compression by the two side stones. Similarly, all the stone pieces are now in compression. So you have made a nice bridge even with a material which is brittle because you are replacing the tensile stresses by compressive stresses. So this example is again from that book. This picture is from book. That's why I am showing you the book again. I am recommending it again and again. Now, in Titanic happened in 1912. In 1921, one of the most famous papers, what I am showing you, is one of the most famous papers, one of the highly cited paper of engineering. If in the history of engineering, top cited papers are listed, this will be among the top 5. This paper. What is this paper? Phenomena of rupture and flow. Fracture. So the fracture idea, the role of crack, which I showed you so simply because now we know, but the role of crack and the role of fracture is a whole field now called fracture mechanics. Just now you have solid mechanics, fluid mechanics, you have a field called fracture mechanics where people study how cracks propagate and grow and how to stop them. So since 1921, it's almost 100 years old paper now, but it is still being cited, and this was the first paper, Griffith, where he showed how to calculate the stress. I told you that the stress which I am requiring for a larger crack is smaller, for a smaller crack is more. So how this happens is Griffith's fracture mechanics. He started that with this paper. Griffith's equation in simple terms and very, very intuitive. I am not giving you the full equation, you will find it in the books and Google. But essentially that fracture stress is inversely proportional to square root of crack size. Intuitively obvious, we saw it in the paper. Larger crack is smaller, it will fracture at a smaller stress. So larger the crack size, weaker the material is, its fracture strength is less. If you plot that 1 by square root pi, it will look like something like this. On the x-axis is crack size, on the y-axis is fracture stress. Now, in this, the true story is you can think that I am the best engineer, I have the best designing process, I have the best manufacturing process, I have produced an object without a crack. Sorry, that is only your mind. That is only an ideality. Everything which you will produce, you will machine. The machine tip is also leaving a mark. That is a crack, the micron size crack. You are polishing. You are polishing using small bricks. That's also a crack. So however much you machine or polish or make things smooth or however smooth the surface looks like, macroscopically, there will be microscopic cracks. So you cannot avoid that. All you have to avoid or all you have to know that whatever crack size on the x-axis you have, corresponding to that, what is the fracture stress? And as an engineer, you have to ensure that your operating stress is less than the fracture stress. This is what the ground engineers of aircraft do. They scan the aircraft body, they scan the aircraft engine components by techniques, special techniques like eddy currents, ultrasonics and all, to measure what is the crack size. And then they know when the aircraft will go up and when the engine will be landing, what will be the stress. So the actual operating stress should be less than the stress at which the existing crack will propagate. So cracks are there, they also find in their ADI testing and ultrasonic testing, they will find that aircraft body is having cracks, but this crack will not propagate at the stress at which we will be flying. So fly. So you are flying in a cracked plane. And if the ground engineer makes mistake in his estimation, you will probably not be there to tell the story. So, the green point is showing an applied stress. For crack side C, the white sigma F is the fracture stress. But if my applied stress is this green stress, I am safe. Fly the plane, ride the cycle. No bicycle is without crack. All you have to do is to do an ultrasonic testing to find a small crack. But that crack, a small crack, will have larger stress, fracture stress. Your riding stress is less. So that is safe. This is where, if you introduce in the cycle tube, if you introduce this crack side and applied stress is less, that crack will not grow. Crack will be there, but crack will not grow, because growing stress sigma F is required. Sigma applied, the pressure of the air in the tube, whatever sigma applied is there, is less than sigma F. So that C, that hole of crack side C, is your leak in the tube. But if the crack size is larger, if the crack size is red, no, if the applied stress is red, then you are in the zone, unsafe zone, and that will be the noisy burst of your cycle. So you can decide the safe, unsafe region if you have plotted this curve of Griffith's equation. And your balloon, whatever crack you introduced initially, itself was unsafe, in the unsafe region, because balloon is also having an applied stress. The pressure with which you have blown the balloon is putting the balloon surface under stress. So it is having certain stress. At that stress, the crack side C is an unsafe crack side, the balloon bursts. Just 5-10 minutes. 5-10 minutes is there? As per 1 hour 15 minutes you had given me. 1 hour is over, I think, but I can use another 15 minutes. Or I can stop if you... Okay, 5-10 minutes, let me see. This last topic, the creep, is that why do glaciers move? Some questions. Why do glaciers move? And how do that old style, nowadays modern bulbs have come, they don't have filaments. But how do filament bulbs fuse? When you say fusion, that is melting. But filaments are made of tungsten wire. The filament melting point is 3400 or so Celsius. If such high current is flowing, which can melt tungsten filament, it will melt many other things in the circuit much before. So, although we say the bulb has fused, the electric bulbs never fuse. And what do Rolls-Royce make? This seems to be a strange question. What does Rolls-Royce make? Yeah? Jet engines, very good answer. Not cars, because the cars are now being made by probably BMW or some other German company. So, why is Rolls-Royce making jet engine? Because jet engine technology, there are very few companies. Rolls-Royce, General Electric, Pratt & Whitney, these few companies. And one of the engines is Rolls-Royce. So the common aspect of these three unrelated questions is that all of them are related to a deformation mechanism which is creep. And you are already seeing creep in front of your eye. One spring is not creeping. Another spring has crept so much that it has gone down. I started with this slide, and it has increased so much in front of your eye at room temperature. So it's creeping at room temperature. Creep is a deformation phenomena. So when you do elastic deformation, more the stress, more the deformation. Hooke's law. When you do plastic deformation, same is true. More the stress, more the deformation. Here is the stress. Am I pulling it? I'm not even pulling it. What is the stress on this? Yeah? Yeah? Gravity, its own weight. Its own weight is there. That's all. And the poor fellow is not able to support even its own weight. So under the weight of gravity, it is so-called creeping. So by creep, what we mean, fuse due to creep, and jet engine life depends on creep. And let me define creep for you. Creep is time-dependent plastic deformation at constant load or stress. Time-dependent plastic deformation. It's elongating as a function of time. You can plot, but force on it as a function of time. Empty. Whatever was its initial weight, that is the force which is acting. And for this spring, I have to pull. I have to apply more force. But this spring is creeping. So this one, when I am deforming, I am doing an elastic deformation and it is following Hooke's law. This one is currently not following Hooke's law, is following creep law and is deforming. So but one spring is creeping, your question should come. One spring is creeping, the other spring does not. Why? The answer is creep is a high temperature phenomenon. But again, the question is, and that's why it is important in design of jet engines, because engines operate at high temperature. But then, this is not a high temperature experiment. Experiment is being done at room temperature. But then the question is, somebody coming from Srinagar and somebody coming from hotter region. Both of them are in the same room but still feel different level of cold. Srinagar particularly is not cold. Delhi wala will say it is cold. So these two, I have selected these two metals of different melting points. And if the melting point is low, that means that metal's capacity to resist temperature is less. So a lower melting point material, even at room temperature, is hot for it. So for the left, although they are at the same temperature, the relative temperature with respect to its melting point is higher for the left spring. And that's why it is creeping. So some more data, I want to wind up, I don't want to trouble you. So what I showed you is one aspect of material science and engineering. I have shown you there can be more aspects, but I have tried to categorize it as three aspects. One aspect is to study electrical and magnetic properties of material. Another is to mechanical behavior. My lecture was focused on mechanical behavior. The third one is chemical and electrochemical behavior. Batteries, nowadays, a very important area of research. And in mechanical behavior of material, what I showed you is elasticity, plasticity, creep, fracture also. Fatigue is one thing which we have missed. So, just one quick slide on fatigue, few slides. Comet was the first passenger aircraft. You can see people are waving and all because it was a new aircraft, first passenger aircraft using jet engines. Before that, jet engines were used only in the World War. And it was a British Airways, British Overseas Airways Corporation, BOAC. So people are waving and all, and it's a good, nice story. But the story again, you know my my obsession with tragedies. All this fanfare ended in an anniversary tragedy from Kolkata. After their first inaugural flight from London on 2nd May 1952, exactly a year after, 2nd May 1953, first crash just took off from Kolkata and fell into the sea. Then people thought that maybe just an accident, but soon after that, accident after accident started happening, and finally it was withdrawn from service. And the worry was that what were the cause of these failures? And what was established that it is because of the fatigue of metal. Metal bhi bechara thak jata hai. So this is a graph which is showing you that whenever nothing is loaded constantly. There is loading, there is switching on and switching off of every machine. Or aircraft taking off and landing, taking off and landing. So there is maximum stress and then minimum stress when it is not being used. So the stress cycles. If the material is not breaking in the first cycle the maximum stress is sigma max. That's the true for all the cycles. And if it is not breaking at sigma max in the first cycle, it should not break at sigma max at any cycle. But that's not what happens. After a certain number of cycles, fracture happens, and this is what is called fatigue. Fatigue, I will end the talk with this beautiful experiment, the biggest experiment which was ever done. The whole aircraft is being tested. So when this worry came for Comet aircraft, that is it due to fatigue? So they wanted to test and to cycle the load inside the plane, they decided to fill it with water and increase and decrease the pressure of the water. Because that is what is happening on a flying aircraft. When it is on the ground, pressure inside and pressure outside is equal. When it is flying, pressure inside is atmospheric to keep the passenger comfortable, but outside is very low. So it's like a pressurized balloon. So it is going in each flight, the aircraft is going in a pressure depressure cycle. Okay, pressurization, not pressurization cycle. So they wanted to create this pressurization depressurization cycle at ground level by water. So they put the whole plane, they filled with water, but water had another problem. That if you fill the plane with the water, so much of weight it is carrying. Actual plane is not carrying that much of weight. So they wanted to cancel this internal weight of water by putting the whole plane in a water tank. So what you are seeing the structure outside, they created a water tank. So water is inside the plane, water is outside the plane in this tank. And then by changing the pressure of the water inside, and they went through that cycle of pressure and depressure which I showed you in the previous slide. Robert de Ballard was one of the discoverers of Titanic wreck. In childhood itself, he decided, बेटा क्या बनोगे? मम्मा मैं ओशन के नीचे जाकर टाइटैनिक wreck निकालूंगा. When he heard this Titanic story, कोई भी मम्मा पापा सपोर्ट करेगा? बोले बात करो होमवर्क करो. So that's what he is saying. All kids dream a marvelous image of what they want to do, but then society, parents, teachers, friends tell that they can't do it. I didn't listen. I wanted to live my dream. So actually, when he grew up, he joined oceanography. He went inside the sea and he could discover Titanic. So live your dream. Thank you very much.
So he has a mic there. So any questions?
Or we please come in front.
So it's fine.
Okay.
So they must have been some ship that have been going through the same path. So what material were they using that the ship doesn't have the same agility as Titanic?
Other ships were going in the same route. So material is undergoing the same difficulties. Like my rubber tube. Rubber tube I have cooled in liquid nitrogen, it has become brittle. But it will break only if you hit.
Yes.
Okay. With Titanic, it hit the iceberg under those conditions. Okay. So obviously, but the imagination was, or the designer's expectation was, that it should not have broken. Because even if the iceberg hits, we have 16 watertight compartments, one or two will break. But it so happened that all those things didn't work and breaking happened. So other ships also, if they would have hit the iceberg, they will go.
So what's the technique that now is being used?
Avoid the iceberg. Avoid the iceberg, but lot of techniques, actually Titanic disaster led to lot. There were other, not only material, I talked because being a materials engineer, I am talking about the materials aspect, business and all. But there were a lot of other ship running policy which was wrong with Titanic. So for example, they didn't have enough number of lifeboats. Because of this arrogance, hubris, you can say that our ship is not going to sink. So why unnecessarily carry so many lifeboats? So only few lifeboats were there. Now every ship by rule has to carry lifeboat capacity for every passenger in the ship. So these changes came after Titanic disaster. Okay. I don't know I have answered your question, but yeah. Okay.
Okay, so I think in the interest of time, on the behalf of Academic Outreach Committee, so we have a token of appreciation for Professor Prasad. So I request Professor Abhijit to present him with a small token.
I'm not going to put this in liquid nitrogen.
So thank you again, Professor Prasad, for the fascinating talk. So we only could imagine that tree fatigue and everything were qualities of human beings, but we could see that now materials also have them, and it was a fascinating. It was really nice to know so many mechanisms behind what goes behind a big disaster. So if you are already surprised or fascinated by the mechanism of how Titanic sank, so be prepared to be even more surprised, because in the next talk we are having with us Professor Abhijit Majumdar, and he will speak to us about the myth of bulletproof jacket. Okay, so a small introduction about Professor Majumdar. So Professor Majumdar holds one position of Ramachandran Jaikumar Chair Professor for Decision Sciences or Operations Management in the Textile and Fiber Engineering Department here at IIT Delhi. He graduated from Calcutta University with a gold medal in textile technology and has obtained an MTech and MBA degrees right here from IIT Delhi. He did his PhD from Jadavpur University. He also holds visiting professor positions in multiple institutes in India and abroad, and has been a distinguished teacher and researcher. So he has guided more than 15 PhD scholars and have authored multiple books and research papers in his career. He has been the recipient of multiple awards, including Gandhian Young Technology Innovation and Eminent Engineer Award, among others. Today, it's our pleasure to welcome Professor Majumdar on stage, and the topic of his lecture is indeed very interesting. Like everyone wants to know about how a bulletproof vest works and how it actually saves hundreds and thousands of soldiers in your country. So welcome, Professor Majumdar. The stage is all yours.
Thank you. Okay. So at the outset, I'd like to extend my gratitude to the academic outreach cell of IIT Delhi, especially to Professor Kurur, Professor Subodh Sharma, and Professor Siddhant. This is the only textile and fiber engineering department in the entire IIT system. There are 23 IITs, and only IIT Delhi is having a full-fledged textile department. So my talk is about myth. So the first question that should come to your mind, what is myth? So myth is something which is assumed to be true, and they have great significance in terms of history, ancient history, but sometimes these myths are not actually true. If you go by science, then you will find that most of these myths are not true. So I try to demystify some of the myths that we have around bulletproof jacket. So here you can see a bulletproof jacket. So myself, my research scholar, and few other colleagues in IIT, we do research on bulletproof jackets. So these are the contents of discussion. Of course, Professor Prasad has given a very fascinating lecture, and I learned so much about the material deformation. And these two lectures are highly correlated, because you will also find that these jackets can also fail due to plastic deformation. Okay. So I start with the evolution of bulletproof jacket, and then I'll demystify the myths of bulletproof jacket one by one. I'll talk about the materials used, then what are the standards that are used for the evaluation of bulletproof jacket. We'll also talk about a very interesting material. You have heard about smart materials. So I give you the example about the smart fluid. Okay, so a fluid that can change from fluid state to the solid state just by the application of shear. So we call it shear threading fluid, and then finally I will talk about future direction of research. So maybe I'll be taking around 40 minutes. Okay. So I'll start with so you might be seeing the IIT professors are always talking about disasters. Okay, so it was Titanic in the first lecture. Now I am starting with this 26/11. One of the most dastardly terrorist attack took place in Mumbai on this day. And you might have heard the name of this KTS chief, Hemant Karkare. He lost his life. And there were a lot of reports in the newspaper that he lost his life because there was some problem in the bulletproof jacket. Although there are some counter reports also that bulletproof jacket was all right. But the first myth is this. Can you check this why it is not working? So I'll talk about the first myth about the bulletproof jacket. So this is me. I'm wearing this bulletproof jacket, but this smile can vanish very quickly. Because if I'm not wearing the correct bulletproof jacket, then the bullet will pierce through. Okay? So you need to wear the right bulletproof jacket to protect against the proper threat level. Okay? So in reality, the bulletproof implies that it gives you complete protection against all kinds of ammunition. And in reality, this jacket doesn't exist. Whatever jacket you can make, it will give you protection against certain threats, not against all threats. So in reality, the real bulletproof jacket doesn't exist. These are bullet resistant jackets. So if you read the lower line, the bullet resistant offer varying degree of protection. So depending upon the level of protection you are looking at, you will have to choose the bulletproof jacket. So now let us try to understand the different levels of threats. So here you can see the 9 mm bullet, then you can see 357 Magnum, 44 Magnum. So these are fired from revolver or pistol. So these are small ammunition. We call them small ammunition. But at the bottom you can see the AK-47. Okay, so this is a big ammunition, and the projectile size is also very big. The kinetic energy is also much higher. So jacket which can give you protection against revolver or pistol, it will not give you protection against AK-47. And when you talk about AK-47, within the AK-47 also there can be different variants. Because the steel, Prasad talked about steel that was used in Titanic. Now steel can have different level of hardness. If you are putting a mild steel inside the bullet, its lethality or penetration power will be lower. With the same velocity, if you use a hard steel core bullet, its lethality or penetration power will be much higher. So it's not about AK-47. People talk about AK-47, but I'm showing the Indian standard. AK-47 mild steel core is just level 2. AK-47 hard steel core is a level 5. And you need to use ceramic to beat AK-47 hard steel core. So the first myth is a bulletproof jacket cannot stop all sorts of bullets. They are resistant against certain kinds of bullet. Now let us look into the evolution of body armor, and it has a very checkered history, very long history. So during the Japanese war in 1905, the silk fiber, the natural silk which we use in our saris, because silk is also quite strong. So the Japanese people, they used silk fiber to develop their body armor. But then the Second World War, between 1939 and 1945, and research is so interdisciplinary, innovation is so interdisciplinary. A doctor of US Army, Dr. Malcolm, he actually developed the nylon fiber based bulletproof jacket, and with that he was able to save a lot of casualties. Now nylon, all of you have seen. In your toothbrush, you have seen the nylon bristles. In your shaving brush, you have seen the nylon bristles. But those are not high tenacity nylon. Those are ordinary nylon. If you can make nylon fiber which is having high modulus and high strength, they can be used to develop this kind of jacket. However, the third generation of bulletproof jacket was developed post 1970s, because this Polish lady, she is from Poland, Tiffany Nolek, she was working in US company DuPont, and she developed the Kevlar fiber. So Kevlar is the trade name given by the US company DuPont, and this fiber is having extremely high strength and high modulus. And with this fiber, we can develop this lightweight, bullet resistant jacket. So I will talk about this fiber and how this can help us to develop bullet resistant jacket. Now myth 2. So we have heard about metals. You have seen the clean behavior of metals, and all of you are using clothing. Okay, these are made up of fiber, textile fiber. And generally the myth is metals are stronger than textiles. Okay, so if you try to develop a jacket, bulletproof jacket, whether you choose textile material or you will choose metal. Textile material, you will not choose metal. Metals are very strong, textile materials are not so strong, but still you are saying you will be choosing the textile material to develop a bulletproof jacket. So, the myth number 2 is metals are always stronger than textile fibers. Okay? Metals are generally stronger but not always, because there are certain textile fibers which are even stronger than steel. Because when you are talking about the strength of a material, you need to check strength to weight ratio. What is the strength of the material and what is the weight of the material itself. And if you take the ratio, you will find that there are certain grades of fiber materials which are actually stronger than the steel. So this is the steel fiber, okay, and this is ultra high molecular weight polyethylene. So ethylene, all of you have heard, and if you increase the chain length, the degree of polymerization, you will get the polyethylene, and here the molecular weight will be in millions. 3 to 10 millions can be the molecular weight of this fiber. And look at the density. Steel is having a density of around 8 gram per cc, whereas this ultra high molecular weight polyethylene fiber has a density of 1 gram per cc. So it is 8 times lighter than the steel, and strength wise they are comparable. So if you have 2 person, one person is very bulky and heavy, another person is agile like me, and if both the persons are able to lift the same weight, obviously I will be the stronger because my weight is less and still I can lift 50 kg. On the other hand, if a person is very bulky and fatty and he is also lifting the same weight, he is not strong. So taking the same analogy, you can understand it here. The steel is strong, but steel is having very high density, whereas some of these textile fibers, they are very lightweight, they can float over water because the actual value is 0.97. So this fiber can float over water and still they can absorb lot of energy. So just look at this strength to weight ratio, we call this parameter as GPD, gram per denier. So for some of these high performance textile fiber, the value is 30 to 40, whereas for steel it is 3. So this is also demystifying the myth that a textile fiber is 10 times stronger in terms of strength to weight ratio as compared to that of steel. So these fibers can actually be used in the bullet resistant jacket. I have those fibers with me, and I'll pass on those fibers, and you can try to break them, okay, without spoiling your finger, okay. So what are the components of bulletproof jacket? So you can see the entire bulletproof jacket. What you can see from outside, this is the camouflage fabric. We call it carrier. Okay, from outside you can see this. What is there inside you cannot see. So from outside you can see this nice multicolored design so that the soldier can hide himself or herself in the forest or in the desert. Inside this you will have this hard armor. This is the ceramic plate. Okay, because the tip of the bullet is very hard. So you have to damage the tip. And to damage the tip you need a very hard surface. So you have this ceramic plate at the strike face. So this is the ceramic plate. And if I open this pocket of the jacket, you can see the pocket here. The ceramic plate is inserted inside. So from outside you cannot see. So this ceramic plate will protect your torso, the important organs of your body. So when the bullet will strike, it will damage the tip. However, the ceramics are very brittle. We have already heard about brittle factor. Ceramics are very brittle. Okay? And when the bullet will strike, you will find that lot of cracks will be created. And to absorb the shock, you need to have some fiber material, some textile material at the back, and we call it soft armor. So a bulletproof jacket is a combination of hard armor and a soft armor. Hard is coming from the ceramic and composites. Soft is coming from the textile fiber part. This hard part will damage the tip of the bullet, whereas the soft part will help you to absorb the energy. So this is how it works. So I was talking about this cracks in the ceramic. So this is the hard armor panel. So when the bullet will strike, you can see that lot of radial cracks will be generated. There can be some circumferential cracks as well. And generally we use these two ceramics, boron carbide and silica carbide, for this purpose. Now you can see, if you don't have a support of fibrous material, then a lot of fragments will be generated when the bullet will strike. So our objective will be to prevent this. So we have seen two myths about bulletproof jacket. Now myth number 3. That body armors can be very, very lightweight. Okay, so people will say, okay, I can have a waist-for-thin bulletproof jacket. And sometimes you will see it in the newspaper also, just like a gimmick, that a person has developed a bulletproof jacket which is weighing just 500 grams. So again, it is a myth, because bulletproof jacket can have different masses depending upon the threat level that you are looking at. So the soft armor, the weight can be something around 1.5 to 2 kgs. So that is lightweight, okay? And then the soft armor can be concealed. So here the left hand side is concealed, and then you can wear a shirt over this. So no one will be able to understand that you are using a bulletproof jacket. But if you are looking at hard armor, which can stop AK-47, the jacket weight will be 8 to 9 kgs. So bulletproof jacket, a real bulletproof or real bullet resistant jacket cannot be very, very lightweight, because you need to use ceramic and you need to use lot of material, lot of fibrous materials. And when you combine multiple layers of those, they will be quite heavy. So this is the Indian standard, and for the medium size, okay, this is the recommended weight is around 9.7 kg. Just think about the soldier. You will have to use this jacket for the entire day. You will have to run, you will have to jump, you will have to crawl, and the weight is around 9 kg. So it poses a lot of challenge to the material science people, so that new kind of fiber and ceramics are developed so that this jacket can really become lightweight. Now if you look at the engineering design of this, the engineering design happens in multiple dimensions. It starts from the nano. Nano is 10 to the power -9. First you have to choose the proper polymer. Okay? So basically you can see these long chains of polymers, and their dimension is at the nanometer scale. Then you need to draw them, you need to orient them, and you will get the fiber at the millimeter scale. Then you will get the yarn at the micron scale, and then you will get the fabric or sheet at the meter scale. So basically the engineering, what you can see at the outer side, actually it has started from the nano level at the molecular level to design this bulletproof jacket. So I'll talk about the fiber materials that we use in bulletproof jacket. So the Kevlar, which was developed by DuPont in 1960s, so it is for para-aramid. So basically it is aromatic amide fiber. Now a little bit of chemistry, I will not go into the details because I am not a chemist also. So you can all understand that these are benzene rings, okay? And then there are different functional groups. So this is diamine, basically paraphenylene diamine, and then here also you have a benzene ring and COCl. By this condensation reaction, you get this amide fiber. So this linkages is CONH, this is called the amide linkages. The other fiber, which is also very strong, is called ultra high molecular polyethylene. So polyethylene all of you understand. And when you join many units of this polyethylene, you get this ultra high molecular polyethylene fiber. So these fibers are extremely strong, and they are stronger than the steel. So the fiber. So I'll show you those fibers, and some of you can actually try just by pulling them. Don't apply too much of force. Then what will happen? Maybe that side. So yeah, so you can just just take it out. Just taste it with your hand if you can break this fiber. Just pull it. Does it break like your thread? No, you will damage your hand if you try too much. Okay, so now what we do, conventional material, but you need to prepare a sheet-like material like this so that you can get material. Okay. So what is done? These fibers are laid in 0 degree and 90 degree. So we call it cross-ply arrangement. Some of the fibers will be arranged in 0 degree, some of the fibers will be arranged in 90 degree. So like this, and they will be bonded by some resin, glue-like element, and you get a sheet. Now to stop a bullet, if you make one sheet, it will not stop the bullet. You need to have at least 30 to 40 layers of such kind of sheet so that you can dissipate that entire energy. Because the bullets will strike this jacket and the professor was able to break those sheets. Now you try to pull this and just see if you can tear this sheet. If you can tear this sheet, then you will get tear these sheets. So this is a materials challenge. Just I have given you a fabric, apply whatever force you have and see if you can tear the fabric. Both roll around. Oddly. See, I have given many lectures with the SPG. Okay, Special Protection Group. Okay, Special Protection Group who gives protection to the VVIPs, President, Prime Minister, and they are really muscular people, SPGs, the black cats. So I have given this thing to them also. I have asked them if they can tear it. So when they have failed, so I am pretty sure that. Okay, so now let us come back to the topic. Okay, how do you test this bulletproof jacket? Can you tell me if you have any idea how will you test this? Yeah, you are right. So we will shoot. So we do research with bulletproof jacket, and for doing research, what you need a lot of funding. Funding is money because the materials are costly. Okay, chemicals are very, very costly. So you need a lot of funding. And we go to different agencies, government agencies asking for those funds. And why this area is so challenging? So this is in a very lighter sense. Say this is a researcher. This is a researcher who has developed the bulletproof jacket. And if you go to the funding agency, this is the person from the funding agency. The funding agency will say, okay, you have developed a bulletproof jacket. You wear it, I will fire at you. If it stops the bullet, you will get the funding. And if it pierces, you will not come to me for the second time. Okay. So this bulletproof jacket testing is quite tricky. And there are different standards. Okay. The most popular standard is from National Institute of Justice USA. This is the most popular standard across the globe. Until 2018, we didn't have any standard in India. But in 2018, we have come out with our own standard, and I'll talk about that a little bit. So here you can see, if you look at this table, there are two regions, green and pink. So in this table there are two regions, green and pink. Look at the weapon in the green region. These weapons are all revolvers or pistols. Okay? And what is the velocity? It is around 400 meters per second. So when you fire a bullet from a revolver or pistol, the typical velocity of the bullet will be around 400 meters per second. But when you come to this pink region, which is essentially AK-47 or snipers, the velocity is more than 800 meters per second. Now all of you are engineering students. If the velocity becomes double, what will happen to the kinetic energy? 4 times, half mv square. So, if the thread is coming from these small ammunitions, you can use the soft armor. There is no need of ceramic. Okay, there is no need of ceramic. But if you are expecting a threat from this AK-47, because the velocity is almost 800 or plus meters per second, you need to have some ceramics. So similarly, this is our Indian standard. So level 1 is for this 9 mm bullet. Now you can see the difference which I have mentioned earlier. AK-47, mild steel core, this is level 2. However, AK-47 hard steel core, it is level 5. And the last one, level 6, is for the sniper. This is a level 6, it is for the sniper. Sniper means for the VIPs, the enemy cannot come in close contact because there will be a lot of black cats around the VIP. So what will happen, the snipers will be hiding 1 kilometer away or 2 kilometer away, and then they will be firing from that place. So this is the sniper round, and here the energy level is very, very high. So even if you are wearing a bulletproof jacket, if the sniper round hits here, I will thrown at a distance of 5 meters at least. So the kind of kinetic energy the bullet carries, even if my torso is safe, actually I will thrown to a very high distance and lot of organs can actually become damaged. So where do you do this test? In India there are only 2 places where you can test this bulletproof jacket. One is in DRDO laboratory in Chandigarh, where you can test this. This is called Terminal Ballistic Research Laboratory in Gandhinagar. And there is another laboratory, Terminal Ballistic Research Laboratory in Chandigarh. And there is another laboratory, Forensic Research Laboratory in Gandhinagar. So what you can see here, the weapon is here, then you have a device, we call it chronograph. This device is having some optical screen here, and it will measure the velocity of the bullet. So this is the first chronograph, this is the second chronograph, and this is your test material. So what will happen, when you will fire the bullet, it is coming out. Now here, when this bullet will cut this optical screen, the time t1 will be noted. Then the bullet will cut the second optical screen, time t2 will be noted. You know the distance between these 2 optical screens. You know t2 and t1. So you will get the delta t. You will know the distance, so you will get the velocity of the bullet. Then the bullet will hit the armor material. Either the material will stop the bullet, or the bullet will go through this. If the bullet pierces through the jacket, then you have the second chronograph to measure the velocity, residual velocity. So pre-impact velocity, from pre-impact velocity you can get the initial kinetic energy, you can get the final kinetic energy, and from the differences you can get how much energy is being absorbed. So this is how we do the ballistic testing. Now another myth, probably the final one. Whenever we test any product, okay, any product you think about, not in terms of bulletproof jacket, any product, and if I say a product is made in India, another product is made in USA, how many of you feel that made in India will be better than made in USA? Raise your hand. Okay, so not much, maybe 10%. Okay, you feel that the Indian product is better than the, you are real patriots. Those who have raised your hand, you are the real patriots, and you really feel that a product which is made in India actually better than the product made in USA. But probably there is one exception, and this is the myth 4. This is Indian bullet resistant jacket, and this is the US bullet resistant jacket. And actually, if you look at the protection level, higher protection is given by the Indian bulletproof jacket, and I will explain why. Why Indian bulletproof jacket that is being used by the Indian Army gives much better protection than the jacket that is being used by the US Army. Because bulletproof jacket should not only stop the bullet, actually 6 bullets will be fired on this jacket at different places. When a jacket is given to the army, before that 6 bullets are fired, okay, on the test sample, and all of them should be stopped. Because if one pierces through, then the soldier will die, and we cannot accept that kind of jacket. So not only the bullet should be stopped, But more decisive criteria is the back face signature. What is back face signature? Because if I am wearing this jacket and if a bullet is hitting here, it will create some trauma, some bruise on my cell, on my body. And the depth of that trauma should not be more than, say, some certain value. Okay? So I'll talk about that, how this BFS measurement is done. So this is kind of clay. You have seen there small kids, they make something with this clay. So this is Roma plastilina clay. We prepare a box and we fill it up with this clay. What is so special about this clay? Hardness of this clay is similar to the hardness of human tissue. Okay? So this can be taken as a replica of human body. Okay? So what is done? The bulletproof jacket is placed over this and then the bullets are fired. Because you cannot fire bullet on a living body. Okay? You cannot fire the real bullet for testing on a soldier. So what is done? We use this clay Roma plastilina, we put the bulletproof jacket on this and then the bullets are fired. Bullets are stopped and then you can see the crater. You can see the trauma that is created and then the depth of this crater is measured. And two important values for the USSR depth, permissible depth is 44 millimeter. So the jacket that is being used by the US Army and in many European countries, they allow the jacket to create trauma up to 44 millimeter. But for Indian forces, because we have Naga regiment, we have Dogra regiment, and their torso, their body size is quite small. Okay? So the standard for Indian Army is only 25 millimeter. And trust me, when you try to reduce the BFS from 44 to even 42, it takes, lot of challenge. It's extremely difficult to reduce the bullet. You can stop the bullet, but reducing the BFS is a very big challenge. And that's why you will find that sometimes you will find that Indian jackets are heavy, Indian jackets are bulky, but the primary reason is this difference. In US, the standard of backface signature is 44 millimeter, whereas for Indian Army it is only 25 millimeter. Now I'll come to our research part. I'll talk about the smart fluid. So this is water, okay, and this is called Newtonian fluid. Okay, this is called Newtonian fluid. And I hope as engineering students, all of you know what is viscosity. What is viscosity? Yours resistance to flow. Okay, so viscosity is basically resistance to flow. So this is a Newtonian fluid, and what happens is viscosity remains constant. Whether I shake it, whether I move it slowly, its viscosity will never change. Okay? So shear stress by shear rate, with which we measure the viscosity, and this is called Newtonian fluid because its viscosity doesn't change. However, you can get certain fluid, you can make certain fluid where the viscosity becomes a function of shear rate. If I apply more shear, the fluid will become like solid. So if it is a smart fluid, you shear it more, it becomes more solid. You shear it less, it behaves like a fluid. Okay? I think some of you have heard about the experiment where you mix cornstarch with water and then you can walk over it. Okay, so I'll show you that video. Okay, so that was just fun. So in a hotel of Kuala they have mixed cornstarch with water in certain proportion, and then you can get this kind of non-Newtonian fluid. So in normal state it will behave like a fluid, it will just flow like water, okay? And if you stand over it, you will sink. But if you keep your feet moving, that is the shear you are creating a turbulence in that fluid. So what will happen, the particles which is there in the fluid, they will agglomerate and they will form like solid-like structure. Okay? So what happens, say I have given you a lot of footballs and I have asked you to fill this particular room. So you can pack them in different ways. So this is one way of packing. The top one, simple cubic packing. The second one is similar to what fruit vendors do. You have seen the fruit vendors, they will arrange their oranges and apples, mostly oranges, in this way. And if you arrange them in this way, what is happening? Out of the total volume of this room, 74% you can cover with these footballs or marbles. Okay, so you have spheres. It may be football or it may be marbles. So out of the total volume, 74% you can occupy with them. And then you can, if you make a arrangement like this, where 74% of the total volume is solid, remaining 6% is the fluid, you can get a shear thickening fluid. So what happens in shear thickening fluid? How do you get this smartness? So this is the equilibrium where the spheres are arranged randomly arranged. Then you apply a little bit of shear. When you apply a little bit of shear, you can see the particles, the spheres or footballs, they are arranging themselves in different layers. There is the top layer, then the second layer, then the third layer, then the fourth layer, and they are moving in their own layer. So one sphere is moving in the second layer, it will not go to the first layer or it will not come to the third layer. Everyone is flowing in their own layer in a very systematic manner. So it flows. It flows without any trouble. Because there are 10 rows and everyone is following their particular row, so there is no log jam. There is no jam in the straight. However, when you apply too much of shear, when you move your feet at a very high rate, what happens? Some of these particles will jump out from their layer. So this particle will jump out from here, it will go there, and then it will form a big cluster. So many small footballs will couple together and they will make a big cluster. When this big cluster will happen, the mobility of the fluid will stop. It will behave like a solid. So this is the science behind the shear thickening fluid. When you create little bit of agitation, basically they will form these streamlines, but when the shear is very high, we call it hypocluster. So all the particles will overcome their repulsive forces, they will combine together, they will make a big cluster, and when you get a big cluster, the fluidity of the fluid is lost. So in this graph you can see when we are creating low amount of shear, the viscosity in Pascal second it is reducing. So this is the shear thinning, we call it shear thinning. But look at this point, then basically there is a step jump. Here you have a step jump. So when viscosity is suddenly increasing, the fluid is behaving like a solid. Okay? So this is how it happens, and we have used this in our laboratory. So we use two simple chemicals to make this. One is silica, that is silicon dioxide, and then polyethylene glycol. We mix them in certain proportion, and then we get this shear thickening fluid. So after that, what we do, you have already seen the strong fabric. I think some of you have seen that golden colored fabric which you are trying to tear it apart, but I think you have not succeeded yet. Okay? Okay. So what we do, here you can see this is your shear thickening fluid, and we pass the fabric through that fluid. So what happens? The fabric is actually soaked. The fabric becomes wet with this fluid. So if fabric is very strong, it is having high strength, it is having high modulus, and then you are treating it with this fluid, which can also behave like solid when the bullet will hit. because the way the bullet will come, the velocity of the bullet is very, very high, 400 to 800 meters per second. So when the bullet will strike here, lot of shear will be created, and if this fabric is coated with that fluid, suddenly the fluid will behave like solid and it will absorb lot of energy. So we have done some experiment with this. So you can see it here in the left hand side. This is a normal Kevlar fabric, and in the right hand side the same fabric has been treated with that smart fluid. So what has happened here, you can see the threads have come out and there is no dome formation. Whereas in this case, you can see because in the fabric you have fibers in both the direction. So here the secondary layers are also sharing the stress and energy, and actually it was able to stop the bullet. So I'll show you two high-speed photography. It is the same fabric. In the left hand side it is a neat fabric without anything, and in the right hand side the fabric has been treated with that smart fluid, and see how it behaves when it will be impacted by the bullet. So the bullet has gone through. Okay, I'll play it again. Look very carefully. Okay, so there was a wave, that is a shock wave that was propagating, but the bullet has passed through. Now when the same fabric is treated with that smart fluid, so bullet is ricocheting back. It is not piercing through the armor, and you can see the wave. Just look at the way the wave is being distributed. The energy is being distributed over a greater area of the fabric. So with this approach, now people are trying to develop this. So this is a live bullet, that 9mm bullet from revolver. Now when these bullets are stopped by this jacket, you can see the lead has come out. Okay, so the tip is now deformed. Here the tip looks very nice. This diameter is 9mm, but now you can see a lot of mushrooming has happened, and actually the lead has come out. So inside this there is lead, and it has come out. So I talked about the materials that we use in bulletproof jacket. I talked about certain myths, like bulletproof jacket can stop all sorts of bullets. That is a myth. Another myth is metals are always strong. That the textile fiber, that is also a myth. That can be true, but that is not always true. And I have also talked about the US jacket versus Indian jacket, and actually our jacket provides much better protection than the jackets given to the US Army. Now what are the challenges? Why do we need young minds, primarily from mechanical, chemical, material science, textile engineering and those fields, because this field is highly interdisciplinary. You need to have a knowledge of something on mechanical, something on chemical, something on material science to develop this. So there are a lot of challenges involved. One of the challenges is developing this jacket for the females. Because right now, even for the Indian Army, a lot of females have been commissioned in Indian Army. But the jacket that they are wearing is still designed for the males. Okay? And due to the difference in body shape and contours, it is much more challenging to design this bulletproof jacket for the female soldiers. So a lot of research has to be done here. Another important aspect is this thermomechanical commissioning. In the past lecture, Professor was talking about the temperature dependence. Okay, so the two metals, one metal can have a lot of heat in the room temperature, whereas the second metal is not showing any heat. If you go to these polymeric fibers, you will find that when you expose them to temperature and humidity, their property will deteriorate. So what is done when some jacket is developed for the army? What is actually done? First, they will fire 6 bullets on this jacket. Okay, all the bullets have been stopped, and all the BFS is less than 25 mm. We call it dry test. That is not the acid test. Then we will test the jacket with thermomechanical conditioning. Thermo is heat, and mechanical is lot of tumbling. So what they do, they will put this jacket inside a big chamber. They will create humidity of 85% and a temperature of 60 degrees centigrade. So they will expose this jacket at a humidity of 85% and a temperature of 60 degrees centigrade for 10 days. 240 hours continuous, this jacket will be rolled like this at that high temperature and high humidity. They will take it out and again they will fire 6 bullets. So sometimes it has happened in our research that the jacket has cleared in normal condition, but when it was exposed to this thermomechanical conditioning, because of that high humidity and high temperature, the jacket has failed. So you can see the BFS, this is from our result. So in wet condition, the BFS was 16.8, but after thermomechanical, the BFS has increased to 19.2. So we need a lot of development in the materials and in structure to develop a real bullet resistant jacket. I'll show you the product which has been developed. This news clipping you have seen recently in newspaper. So this is the soft armor, soft body armor developed by our group, and then it has been incorporated with the ANVESHAN hard armor developed by our colleagues from mechanical engineering. So this is the so-called the lightweight jacket that is available in India till today. Okay, so this is the product which has come out from the collaboration of IIT Delhi and DRDO. So now the conclusion. The design and development of bulletproof jacket is an exciting area of research for the engineers. The bulletproof jacket is not a panacea against all threats. Don't think that I am wearing a bulletproof jacket so I am safe. No, it is not a panacea to all kinds of bullets. You need to wear the right kind of bulletproof jacket to get the right kind of protection. Reduction of weight, because right now the jacket weight can be as high as 9 kg. So the reduction of weight and meeting the BFS pose the real challenge, and novel materials and structures are needed to meet the aforesaid challenges. Okay. So this is my research group. So a lot of PhD students who have contributed to this research, and one of the students is present here, Jyotirmoy. He showed you the material, and I am thankful to my institute for generous funding and support, IIT Delhi. This is DRDO, IIT Delhi Center of Excellence, CSIR, DST who have funded. My all-weather friend and colleague, Professor B.S. Butola, Dr. Rahman, who is the director of JATC, Professor Naresh Bhatnagar, who develops the hard armor and currently the Dean of IRD, and Dr. Devarati, an ex-DRDO scientist. So I acknowledge their contribution and support in this journey. Thank you so much.
It was very nice to see that finally from one of our finest labs here in our institute, we can make some products which can actually challenge those the best from abroad, like in the US. So we still have some time for questions. So please raise your hand if you have any questions, so we can take them one by one. Any questions?
If it's really that difficult to make a bulletproof jacket according to a woman's anatomy, like why can't it be made exactly like how it was made for a man and like for a woman?
Yeah. It's not that difficult, but it is not that easy also, because what you have seen the material, it is fiber reinforced thing, and especially when you have a contour of your body, arranging the ceramics in that form, and then I can apply a lot of pressure on a very surface. The pressure distribution is very, very even. But once you give me a contour, you are applying uniform pressure when I am making this, say 50 layers or 100 layers of those kind of shapes, I am arranging them on a contour, it becomes challenging. It is not that simple, okay? Because in materials we call it a shear property. Okay, this fabric has a good shear property, but that sheet, it doesn't shear that easily. Okay, it will develop lot of curls when you put 50 layers and when you try to arrange them in the form of a contour. So there are certain design challenges, but yes, it can be done.
that is something to, that it is possible.
Yeah, of course it is possible.
That is something to look forward to.
Yeah, sure, it is possible. Yes, it is possible.
Thank you.
Thank you so much for the wonderful presentation. I have one question. In one of the videos you showed fabrics that were subjected to bullet impact.
Yeah.
In one of the slides it was applied to the fluid. So sir, is a mechanical characterization test or data available with us?
Yeah. We have all those data. Mechanical characterization means, see, in terms of tensile strength, in terms of how much energy those two fabrics have absorbed, those data are available with us.
So like in user you can replicate that data in simulations.
Yeah. Actually, some students in chemical engineering, they have done simulations also. Some PhD students in chemical engineering, they have done simulations with this data also. So it is possible, those data are available with us.
So I have some questions I will talk about.
Yeah, sure.
Thank you.
Testing and things like artificial intelligence which can be incorporated for the better testing.
Okay, so my knowledge in AI is, very shallow. But, something what we have done, actually one group of undergraduate students in IIT, what they did, and we filed one Indian patent with that. What we did, when you are hitting the soldier, it is not really the artificial intelligence, but more into the communication side. When the soldier is being hit in the battlefield, okay, he or she has to be shifted very quickly. They must be evacuated within few minutes. So what they developed, they use some conducting threads. So threads which can conduct electricity, and they made a matrix over this. Okay. So when the bullet will strike, some of those threads will break. The circuit will stop, and then the message will go to the mobile phone in the form of SMS, and so that just to give this message to the war room that okay, this person has been hit and he or she should be evacuated. So we said it is another level of smartness, but yeah, I'm pretty sure with AI level many more things can be done. That's one more question.
Since non-equivalent fluids.
Yeah.
So fluids in general, you think of gases and liquids, and over there you demonstrated one example of a substance, and you just showed a video to us. So sir, my question is that we have a very good, which came up to my mind, for example, quicksand. Whenever we visit our deserts and everything, and sir, as a chemistry student, I know quicksand is a colloid. It's not actually what a liquid is. It's just sand, and you have water, and for the right temperature conditions, it forms kind of properties of non-Newtonian.
Sir, my question is this, as right now we are talking about with jackets, but there is many events if you have saw in media that media persons was killed by bullets. So how this invention is successful that still there are many media that we are talking about Israel and Palestinian war. Around 2 years ago, there one Palestinian were killed by he wearing a jacket. So how can it be successful?
Okay. So I think you were. I have shown you this ceramic plates. So you have a ceramic plate just to protect your front. Okay. At the back side, if you look at the back side, the protection level is always low. So if you are if you're receiving the fire on this side, only you are safe. But if it is hitting here or if it is hitting your back, then you are no more. So it's not possible. And then also, we give a protection in the joint. But what happens? It reduces the agility of the soldier. So what they will do, they will just remove this so that they can move. And if something hits in the vital organ, again they will be killed. So you cannot protect. Look at this throat part. Here there is no ceramic. In the throat part you have some textile element. So if it is AK-47 and it is hitting here, it will just pierce. So when you are looking at this jacket, this 360-degree jacket, there are different levels of protection at different places. The maximum protection is here. much more. That's why you will find a lot of soldiers is actually being killed when they are in the battlefield.
So if there are no more questions, then let's thank Prasad Majumdar once again, and we have a small token of appreciation. And I request Professor Prasad to do the honors.
You should be implemented.
As we come to the end of this session and program, so a big thank you to all of you for taking out and attending this event. And I think some of you have come from far off places, from NCR and other places. So thank you once again. And so we are actually planning to have this event like once a month at least. So we'll keep you posted. We'll keep the coordinators of your institute posted about our future events. And you can also find more information about our events if you follow our Facebook and I think Twitter and Instagram pages. Okay, so we post regularly about our events there. So you're free to follow those pages. And you can also get some idea about our academic outreach from our website, which you can find on our IT Delhi webpage. Last but not the least, we have some small snacks and tea for you downstairs in the ground floor, just in front of a seminar hall. So if you just leave the hall from this end, you can just take the stairs down and you can see the table. So you're all welcome to have snacks and tea here. So thank you and see you all again.
उधर अभी आप भी आ जाओ साथ में।